So our next speaker is Valia Allori. She's a professor of philosophy at Northern Illinois University, right? So please.
Okay. Hello, everyone. Thank you for inviting me. It's a pleasure to be here. So, so in this talk, what I'm going to talk about is many words and the issue of scientific realism. So hopefully I will not run out of time. So let me just put this forward. All right. So the usual story with which people is presented to the many-word theory is through the measurement problem. So the measurement problem is the problem of dealing with unobserved macroscopic superposition. You all know about it. And so one popular way of describing the measurement problem is by saying that the three following claims are incompatible. The wave function evolves according to the Schrödinger equation. The wave function provides a complete description of all physical systems, and all measurement have results. And so the idea is that, the usual solution of this provided by the von Neumann rule is too vague because it involves, the notion of measurement or observer and stuff like that, so it's kind of vague. So when people want precise solution of the measurement problem, they say, look, these are, most popular options. So you can deny the first, you can deny the second premise or the third premise, and you end up with the different proposals, right? The many words, the spontaneous localization theory, the pilot wave theory, and the many word theory is the one that's supposed to deny the third, right? So allow for different, all measurement happening. Okay, so why, what's the deal with scientific realism? And this is connected to things that, Lev just said, right? The definition of what science is. So I'm probably I didn't know that he was going to say that, but it's just like, I think it's going to be fit right in exactly where, why many words is not the consensus. I will try to provide a, one possible answer. So what is scientific realism? Very roughly put, the idea is that scientific theory, and in particular fundamental physical theory, are to be taken as approximately true and can guide us in our metaphysics. So meaning what? Meaning that they're going to tell us what tables and chairs are made of, and things like this. So the usual story is that quantum mechanics, as you find it in physics books, is incompatible with scientific realism unless you solve the measurement problem. So that the problem to solve in order to have a theory which is viable to a realist interpretation, something that can tell you about reality, something that can be used by the scientific realism. Many word Bohm mechanics and GRW are possible solutions of the measurement problem. They're satisfactory up to a point, right? And usually what happens is that people they're gonna say, look, they're in a sense, right, equally satisfactory in solving the problem. Everybody's their own preferences, but they're equally compatible with scientific realism, right? We just said, we need to solve it like this, like that, like this. Okay, and so people disagree about which is to be preferred, right? Because in a sense, right, this is what people usually say, you just list the pros and the cons of each theory, and basically people are just weighting this more important than that, and so they pick their own theory. Okay, so here's a a very partial list, right, about that is listing these pros and cons. So the many word theory, the pros are just like very, it's the simplest and most straightforward, the one that requires least modification of the formalism. Some people argue that it's the most local. The cons are that, it requires a kind of a revisionary metaphysics. There is a problem of probabilities, the problem of the Bohm rule, the fact that the wave functions in configuration space. These are the list of problems that have been put forward by in general that, of course, many more people are trying to solve. The GRW theory, people just say, yeah, sure. I mean, it just seems to be more compatible with relativity. At least that's what people are saying, right? And the cons are just it's stochastic, right? It's ad hoc, right? It's the wave function configuration space. The tidal wave theory, people are arguing that it's simpler, straightforward, and just like the cons are just, well, it's redundant, right? Why do you need the particles if all you can do is with the wave? It's explicitly non-local, it's too classical, and so on and so forth, right? So the idea here, the usual story that people are told is just, look, you want to be a scientific realist? Yes. So what do, right? Oh, you have to solve the measurement problem. Oh, okay. So how can I solve it? Oh, you can solve it by many words, GRW or tidal wave, okay? And then, of course, each of them has its problem, right, and advantages. And the disagreement is just like, okay, fine. So you have the pros and cons, right? Depending on how you weight them, right, you will have your favorite theory. All right, so this is a picture of a book by David Deutsch in Italian, right? So so that's where I did my undergrad, right? So that's the first book that I've ever read on quantum theory. I found it in the library, and I mean, I was just immediately hooked, right? So that's his fault that I'm in the field of a foundation of quantum mechanics. And so I really loved many words at the beginning, but then I somehow started to really fell out of love with that for a variety of reasons. There is a sense in which this is partly of the biography of what I find kind of unsatisfactory in many words. But but it's my love, my first love, right, in foundations. All right, so what I'm going to try and convince you about, right, which is basically what already some kind of, the same thing that Lev already admitted, but, maybe not all many words will want to agree with that, is that actually when people are, going to pick out their interpretation, their quantum, I don't like interpretation, let's just call it their quantum theory, right? That they're actually picking one or the other because they have a different view about what type of explanation they want, okay? So, and this somehow leads them to endorse a particular kind of realism. So there is a sense in which it's not true that all solutions of the measurement problem are equally compatible with scientific realism. What actually happens is that people are looking at different problems and finding their different solution, which fits well with their view of realism. So, and I'm just going to leave it at the end with some kind of a motivational problem, right? Because it seems to me that the type of explanation that the many-word theory privileges leads to a type of realism which is so weak that it makes you wonder, why did you ever get into that theory to start with, right? So you wanted to solve the measurement problem, you end up with. Okay, so let's see where we are at, until 11. So. All right. So there is this view which is called the primitive ontology view, and which I partly contributed to develop, which is a funny name, so you shouldn't be really, consider that too much. Don't care about the name too much. But the basic idea is that in order for a theory to be satisfactory, it has to have some sort of a three-dimensional ontology, right? So that's the main claim of the primitive ontologists, right? Just me. That's what I'm going to say, me, right? I am going to say that in order for it to be satisfactory, a theory has to have this three-dimensional ontology, right? Because of that, and I'm just going to explain why in a second, right? Three-dimensional ontology means like, particles in three-dimensional space, fields in three-dimensional space, events in three-dimensional space. Okay. Okay, so if that's what you want from a theory, then it's not enough to solve the measurement problem, right? Because there are ways in which you can solve the measurement problem without having a three-dimensional ontology, right? So if you solve the measurement problem in another way, right? In one, one denying one or denying three, right? Just going many words or going GRW, you don't have to add anything. You just say, oh, the wave function, measurement do not have results. You're splitting the words, right? Or but the wave function is still the ontology, which is not in three-dimensional space. Or you just say, oh, the wave function doesn't evolve according to the linear Schrödinger equation, right? So nothing has to do with the ontology. Only the second one, right? Just say, oh, I'm adding something, right? Which is going to be the most important thing in the theory, namely particles, is in root number 2. So, what the primitive ontologists are saying is that what you want, right, in order for a theory to be satisfactory is for the theory to be, quote, complete. Okay, in the sense that it needs to have this three-dimensional ontology. Quantum mechanics by itself doesn't have it because it just has the wave function, which is not in three-dimensional space, so I used to supplement it with something, right? So, and that's what, the pilot wave theory does. So, but why is that we are fixated on this thing, right? So this is the reason that I find, more pressing. This is the reason why I think that's, we need this primitive ontology, we need this three-dimensional ontology. Because I personally favor, and I think I'm speaking also for many other people, a kind of a constructive explanation of the phenomena, right? This use of constructive, it's due to Einstein, which was just like dividing between constructive and principle theory. Constructive explanation, very roughly put, is the idea that macroscopic objects, right, are made up, right, of microscopic entities, right, which is, in this case is just like, whatever the primitive ontology, the three-dimensional ontology of the theory is. And macroscopic properties and macroscopic behavior are explained, right, in terms of the dynamics of the microscopic, right? This is just like, think about the kinetic theory explaining, the thermodynamic phenomena, or, classical mechanics explaining, macroscopic phenomena, right? I mean, classical mechanics, particle moving around, right? And on all the properties at the macroscopic level are in terms of the microscopic dynamics, right? So constructive explanation is supposed to be good, right? Because it explains why, right? What is, so to speak, the mechanism behind the phenomena, right? Why the phenomena are happening, right? In terms of compositionality, right? Stuff, right? Bigger stuff made of smaller stuff, right? And microscopic dynamics. Okay. Oh my gosh, what did I do? Okay. So if a theory has a if a quantum theory has a three-dimensional ontology, then the theory, then the theory can explain the microscopic phenomena like that, constructively, right? So, I mean, the microscopic ontology is three-dimensional space, right? It's in the same space as the macroscopic object, right? Three-dimensional space, that's the fundamental space, right? And, just very straightforwardly, just like in classical mechanics was done, you can just try and extend the explanatory schema to the quantum domain as well. If instead a theory is only the wave function in high-dimensional space, then it's not straightforwardly the case that, tables and chairs are, so which one is the fundamental space is one question, right? I mean, people have provided with different answers. So you have, the fundamental ontology is this high-dimensional space, right? The appearances of the phenomena are in three-dimensional space. So what's going to be your ontology? Something in 3 dimensions already. So, I mean, there is a story to be told. It's very unclear at this stage, right, what kind of explanation you have and whether you can extend, if you want to, the constructive explanation that you straightforwardly have with the 3-dimensional fundamental ontology. So GRW0, which is just like, GRW with only the wave function, in many words, do not explain the macroscopic phenomena in that way. This is a very important reason for why the primitive ontologists, I mean me, think that this theory are inadequate and they really cannot, I mean, they're unsatisfactory and need to be completed. Okay, fine. Okay, so let's just move to the proponents of the many-mode theory. Okay, so this is what it seems to me, and of course, I mean, I may well be very wrong about that. So what kind of explanation do they seem to favor? Okay, so it seems like, coming back to Einstein's distinction between constructive and principal explanation, they seem to favor, the other side, right? The principal type of explanation. according to which macroscopic phenomena are accounted for in terms of principles, right? So you have this principle, and what the principle does, it tells you what can happen and what cannot happen, right? So for example, in thermodynamics, there are the principle of thermodynamics, right? Principle 0, 1, 2, 3, whatever, right? So for example, the principle of conservation of energy is will tell you that phenomena that do not conserve energy will not be observed. Okay, so it tells you what you should expect it's going to happen, right? But not really why the principle holds, right? They don't tell you, where the principle is coming from. It's a principle, okay? So there is a sense in which this, to me, really reminds me of the fact that what's happening with this kind of principle theory is that they are saving the appearances, right? So that's what they do, right? So they just like systematize, right, what you observe and say, I observe this phenomena, right? In all this phenomena, energy is conserved, right? This is, explained by the principle that energy is conserved, right? All right. So what I'm going to do is not try to argue that principal theories are, better or worse than, constructive theory. I'm just going to simply put that out there, right? That this is the type of, of explanation that these scientists are providing and seem to favor and seem to be enough, right? In contrast with the other people. So I'm not going to read this all. But the point is that, okay, so it seems to me, going back to many word theory, that what they're using, right, one way or another, is they're using these principles, right? So you're just going to use, the coherence is going to be important, right? And just going to be a rule when you're going to observing classical words. There's going to give you a rule about the different branches, how they decompose. They're going to give you a rule about how you should adjust your credences and probabilities. They're going to give you a rule about, why this and why that. So it seems like what's going on over here is not like, when you had a three-dimensional ontology and just say, look, there are this stuff that is moving around according to these laws, and you can understand why this phenomena at the macroscopic level, it's a certain limit, the equation goes this way and goes. No, what's going on here is that, there are these principles that what they're gonna do is, take care of what you observe, right? They're gonna, systematize, right, and account for what you observe at the macroscopic level. So here's a, schema of what I just said, the primitive ontologies, what they need in order for quantum theory to be compatible with scientific realism. They require the solution of this completeness problem, right? You need to, meaning if your theory doesn't have a three-dimensional ontology, you should have it, which is tied to this type of explanation that I've called, following Einstein, constructive. Instead, the many word theory, together with this bunch of other people, instead, they say, no, we can also solve the measurement problem precisely in other ways as well. So, they're open to more type of explanation. So, the primitive ontologies are stricter, right? Either you have that or you don't. If you don't have a three-dimensional ontology, you're done, right? Not compatible, not explanatory. Right? Instead, the principal explanation people are more open, right? Just say, okay, the important thing is that you solve the measurement problem precisely, namely without vague concepts. Okay, so what? So what's the point? All right. Yeah, the problem with that, though, is that, people who like principal theories are often instrumentalists, right? So we started off with this idea that we wanted to be a realist, but then we ended up with this kind of explanation that somehow gets us to be instrumentalist. Okay, right. So why do I say this? Okay. Because, you probably know already this, but the proponent of the information theoretic approach by Bob and Petoskey, they are, explicitly endorsing principal theory, and they are, they claim to be realists, but they are, considered by all, most instrumentalists, right? So So the idea of the information theoretic approach is that quantum statistics are covered by the constraint that Hilbert space structure imposes on quantum dynamics. Hold on a second. Okay. The wave function, right, has the role of describing the agent's preferences, the expectations, right, about the measurement outcomes, right? So basically, these are the principles. You can list of these principles, right, and then they are what they are, right? So they explicitly characterize the way of providing explanation is a principal type of explanation, right? Explain is to tell what to expect. Explain is to explain how nature works. And I mean, they also argue that principal explanation has to be preferred by constructive explanation, but I'm not going to go into that. I mean, I don't think it's needed for what I want to say. I think that's not even true. I mean, but that's okay. Right. So, I mean, what happens is that they argued in virtue of the fact that, I mean, they say that, you know, I mean, they are realists because, I mean, they have another, their own definition of realism is that to provide a, you know, an objective description of the phenomenon. That's an objective description, and so why do you need more, right? Measurement at the fundamental ontology, right? There is no need, actually, to solve the measurement problem. This is just like a mistake, right? The von Neumann rule is just going to be enough, right? The only problem that needs to be solved is to have the theory to be empirically adequate, right? I mean, standard quantum mechanics, you know, with the Schrödinger equation alone is not empirically adequate because it gives give rise to, you know, macroscopic superposition that we do not observe. But if we add the von Neumann rule, what's the deal? What's the big deal? Right, we are done, right? I mean, it correctly systematizes the phenomena? Yes, sure, so that's it. Right? But people do not usually like that. I mean, we started off with exactly like this. It's not precise. It's not, you know, that's not what we want. Right? So, I mean, you're borderline instrumentalist if there is something that, you know, makes sense of that. I mean, of that word, borderline instrumentalism. So most people would be, you know, considering this kind of, you know, approaches more like instrumentalist than realist. Okay, so we are at this stage now. Okay, primitive ontology, constructive explanation, and they're required to be extremely strict about what you want from a theory. And so the measurement problem, I mean, I don't know. So when we talk about, when we have papers on the primitive ontology, we always focus on the measurement problem. I came to believe that this is actually a mistake, right? We shouldn't really focus on that because that's actually not what we care about. We care about is that requirement, the completeness problem, right? So even if you solve the measurement problem in other ways, still the theory is not going to be satisfactory. Instead, the many-word theory, the GLW people, they say, no, we need to solve the measurement problem. You're requiring too much, right? But in that way, they commit themselves, right, in being that open, they commit themselves to, you know, a looser type of explanation, what I've called the principal explanation. But then, of course, right, the danger is just to fall down into this kind of a more anti-realist views, like the IT approach, the information theoretic approach, right? They're just going to say, oh, no, right, we don't even care about the measurement problem. There is no measurement problem. There is no need to solve the measurement problem because we just have the von Neumann rule, which makes the theory empirically adequate. There is nothing to more about that. So this is also kind of a principal explanation. So I do believe that, I mean, maybe not every kind of many words that want to distance from that, but some probably do. The information theoretic proponents are, in a sense, I mean, if we're going to call them realists, they're just going to be extremely weak realists. And to explain in terms of principle is enough, right? Means that recovering the macroscopic data is enough. The many-word theory also explains in terms of recovering the data using constraint, right? Enforcing by suitable principles. And this is as opposed to explain why this principle hold and to explain the macroscopic phenomena in virtue of the microscopic phenomena. So it seems to me that also the many-word theory are kind of a weak realist like the information theoretic approach proponents. Instead, the primitive ontology are much stronger realists that require, you know, this dynamical mechanism in terms of three-dimensional stuff moving around. Okay. So that's the robust realism. I mean, I don't know, weak realism and weak realism. So that's the different type of realism which is involved. So, right. So, I mean, in order to, so this is probably, I mean, this is the way in which I see that people are disagreeing because, people favoring Bowman mechanics, they will just go for, solving the completeness problem, having the three-dimensional problem, while instead people, the many word theories for sure, but also the GRW people, they are just like, more, they have in mind this type of realism, which is much weaker. So, and they tend to consider as living possibility things that, people which are more robust in the realist perspective do not think it's possible. It's enough. Okay, so let's call just like for, I think I'm almost done. So. The realist problem, let's define it as the problem to make quantum mechanics amenable to this realist interpretation. The primitive ontology, think of the realist problem is actually the problem of having a three-dimensional ontology. So if it doesn't have, you have to complete the theory. And then the information theoretic approach people, they think it's like the problem of empirical adequacy, correctly systematizing the data. And the many word people, they think it's the measurement problem, precisely solved, right? Dealing with unobserved macroscopic superposition, not in terms of the von Neumann rule. So the von Neumann rules, according to the IT, they can do it. And so the problem now is, okay, so why is that the von Neumann is not enough for the many orders? So why should they care about the measurement? Should we care about, so if we are many orders, so why should we care about, solving the measurement problem precisely? So the measurement problem is from dealing with unobserved macroscopic superposition. It's about the macroscopic level, right? Unobserved macroscopic superposition. A realist which is interested in the dynamical of the microscope, of the in the explanation, right, of the macroscopic phenomena in terms of microscopic dynamics, right, should not care about it, right? The instrumentalist who cares about principal type of explanation also should not care about eliminating this macroscopic superposition precisely, right? And in fact, that's exactly what the people, Boom and Pitofsky, say, right? So it's unclear to me why the many word people should care about it. So here's a possible reply, and this is my last slides after this. So one could just say, oh, well, the von Neumann rule just involves this notion of measurement, right, and which is totally vague, right? Yeah, it's vague. But so is the appeal to the coherence, right? All this business about branching. And so why should it matter if it's vague, if all you care about, after all, it's just recovering what you should expect, right? Oh, that's because it's important to unify the dynamics at the macroscopic and the microscopic level. Could be another answer, right? I mean, a follow-up. But why is that important? Why is the dynamics important after all? I mean, where else is it important in your explanatory schema? You just have, principles. I'm not saying that I'm just questioning, right? I mean, these are open questions, I don't know, right? Another follow-up could be, well, we do not actually employ a principal type of explanation, right? I mean, that's not what you do. You're mischaracterizing what we're doing, right? I mean, I am, but I mean, that's not, my intention at all. It's just like trying to make sense of this. One thing, though, is that, this is not dynamic. Your explanation that you provide is not dynamical either. You do not explain the macroscopic behavior in terms of the microscopic behavior. So, and actually, I mean, unless you are a certain kind of many worders, right, you don't even have three-dimensional entities, right, at a macroscopic leple, right? So all you have is the wave functioning configuration space. Right. So I've argued that the many word theory, by solving the measurement problem without a three-dimensional ontology, favors a principal type of explanation. To explain is to explain the appearance, to save the appearances. This is what the IT proponents do, and they are pretty much instrumentalist. They claim that there is no need to solve the measurement problem precisely in virtue of the fact that all it needs to be done is saving the appearances. So why doesn't even need to solve the measurement problem? If there is no need to solve it, then there is no need to come up with a theory like the many word interpretation, right? So why we should believe in such a theory? So I'm just going to leave it with this, very pessimistic question, and I thank you for your attention.
Thank you, Valia, and thank you for leaving time for a discussion. So let's make good use of it. Just before you ask your questions, there are microphones here. It's working. And start asking once the microphone gets to you. So we have here, and then David and Simon.
Okay, be gentle.
Yes, so, well, I find several troubles here, but it's not hard to know where to start. But first of all, about decoherence, one of the last points you made. Bohmians also need decoherence, right? I mean, Bohm was the first one who referred to decoherence, or who talked about decoherence, rather, in terms of measurements. So if that is way vague, then there is no way out of that for anybody, right? So I don't see the point there at all.
Okay.
We're all stuck there.
Right. So yeah, let me just say this, I mean, but at least, right, it seems to me that the appeal to the coherence comes to a point in which you have the explanatory schema, but you don't have the vagueness at the fundamental ontology at all. I'm all for vagueness, in the process of, deriving macroscopic phenomena, but I'm not okay to have vagueness at the fundamental, postulate of the theory, right? And it seems like if you are, yes.
I don't think that the wave function is a vague notion.
Right.
So I don't think there is any vagueness in the starting point of many worlds either, for that matter. It's just as well defined. But I see your problem, and that's because much of many worlds have not really well defined, have not defined at all what the wave function means, which I then propose my own definition of that, which I have the opportunity to talk about in the latest talk.
Oh, that's going to be great.
But I see the point from many of the criticists of many worlds, that it depends on that the many worlders haven't really defined well what they talk about.
Yeah, okay.
I understand the misconceptions.
Right, I will looking forward to that.
Then?
Hello.
David, Valia, and Simon.
I love the talk because it explains very well the kind of critique that you and other people are making. But I think that, at least this is how I understand, we start from principles, and we also take a constructive approach to construct those tiny things that the Legos that you presented from principles, and then use those to build and to give an explanation. For example, you mentioned that, and I agree with you, there is a first level of explanation in the many worlds interpretation. You look at the macroscopic level, you see the pointer state, and then you say, okay, so we are either in the branch where the pointer indicates this result, or in the branch where the pointer indicates another result. And this is a first level. But people who are interested in many worlds interpretation also go deeper and try to build Legos to tell a story of what happened at the microscopic level. Lev, for example, has many experiments in which he combines, he uses Yakir's views on the two-state vector formalism to identify what happens in between the measurements with the particle, and to cast it in as an explanation of the microscopic from the point of view of the many worlds interpretation. This is my understanding, at least. I saw some, so he has some work in which he compared different views, different interpretations of quantum mechanics, what they say about what happened with the particle in between the measurement, the observed particle. So I think that this is right way. If we want to do science, we start with principles, and it's very useful to build model for particular situations, to have a constructive approach, but constructive approach alone is more like modeling or like engineering, while principles are very important for science, and I think we both agree on this.
Yeah. Okay. Yeah. So I mean, my talk was actually kind of, I mean, I put a provocative twist in that, right? So I mean, I didn't argue at all which one we should prefer. I just wanted to say, look, I mean, according to me, this is really what's going on, right? We're really disagreeing about this. So we'd actually talk. We should agree that we disagree, and I mean, but I mean. So of course, right, you just say, okay, right, I mean, we start from the principle, right, and then from the principle we can somehow come up with a microscopic word, which is three-dimensional, and then use, again, the same tools that we used before, right? Sure, I mean, that's probably the way to go. But I mean, sometimes I get frustrated when I talk to people and we talk past one another, and then finally I think that I kind of understand why we clash, right? Namely because we have this different intuition about what we actually should be doing. Right.
So you formulated very well the problem, because I had the same problem, and I think we will solve it in the next days, because we can...
Oh, wow.
No, I mean by the interaction to understand each other better. Thank you very much.
Okay, thank you.
So I think it's, I think you're right that there are different conceptions of what counts as a solution to the measurement problem, and I suspect you're right, it's quite tied to the kind of explanation that's wanted. Let me suggest that the kind of explanation that's being looked for in Everettian approaches isn't quite well captured by the principal clause. Okay. I think it's more something like a structural placeholder. And I mean, just to illustrate what I mean, take your example of the conservation of energy. So if I want to say, look, why is energy conserved? I'm not going to say, well, it just is. Go away. I'm going to say something like, well, you know, I think we have a very good answer why energy is conserved. Energy is conserved because dynamics is time translation invariant, and we have the Noether relation between symmetries and conservation laws. Now, if you want to know why is a specific physical theory time translation invariant, and therefore why does that specific physical theory conserve energy, now we can have a very detailed, constructive, if you like, discussion of exactly how it is that we can identify such and such symmetry structure in its Lagrangian or its Hamiltonian or however it's formulated. But we'd be missing something really important if we said, well, the reason why energy is conserved is because in Newtonian mechanics we can prove this quantity is conserved, and in the Klein-Gordon theory we can prove this quantity is conserved, and general relativity with asymptotically flat boundary conditions, this quantity is conserved, and so on and so on. There's a structural unity to what's going on there. So I think similarly, in the Everett case, decoherence gives the branching structure. That's the structural answer. That's saying what you need the detailed, specific dynamics of your theory to provide for you. If you want to know why, in a particular dynamical context, we've got decoherence and so we've got branching, now there's no hand-waving there at all. I mean, there are precise error bars, but now there's a very detailed technical series of conversations in non-equilibrium quantum statistical mechanics. And I think from that point of view, what characterizes a lot of the Everettian approaches is a neutrality as to the particular quantum theory in discussion, under discussion. But that's always going to be a placeholder for the fact that the particular quantum theory under discussion, which is going to be domain relative, is going to have to deliver the goods on decoherence theory.
Okay. Yes. Okay. Good. Great. I think that's exactly what I was asking, right? So I mean, I was, pushing towards that one and said, no, hold on 1 second. I mean, we are just like a little bit different, right? And I think that, yeah, that's exactly what I wanted to hear. So thank you. Appreciate it.
Yes,
Hello.
So, I do have a question. Nobody was actually asking you a question, but I will start off with a remark, namely that I think your talk is excellent vis-a-vis Lev. So, Lev, I do think you've got something to answer for here, because it's exactly Lev's take on many worlds, whereby everything is analyzed in terms of experiments, high-level macroscopic stuff, but I think your critique really kicks in. But if, on the other hand, you favor decoherence theory to
understand and analyze the structure of branching, how it arises, when and where, typically, as David was saying, at a semi-microscopic level, then I think it's a very different sort of animal, really. And I just wonder whether you distinguish the two types of many worlds. But here's my question. You did seem to say at several points that there's a problem with recovering objects in 3 dimensions. Well, you did. Now you're shrugging.
I did
I don't know what to think now. So, but this is my question. I mean, suppose you were convinced that indeed we can recover objects in moving around in 3-dimensional space. Would that have made any difference to your talk at all? In which case, why did you mention it?
Right, no, I said, in the slide it said, right, you do have problem of trying to recover that. I mean, especially what I said, especially if you believe that the wave function is an object in 3-dimensional space, right? If instead I think about something else, right, you know, and you do, I mean, there are ways, I mean, even if you have this, you know, wave function in configuration space, Alisa, and David Albert, they have their way of having the, you know, the object in 3-dimensional space emerge. However, my problem would just, no, it's not my problem. I mean, this analogy, what's going on in postulating 3-dimensional objects is that still the kind of explanation that you do have seems to be, you know, extremely convoluted to me, right? And so I tend to think of those as more akin to principle type of explanation than to constructive type of explanation. So since you do have this constructive type of explanation, which is straightforward, so why simply not go from that? So you may arrive to extract, so you may get 3-dimensional objects, you can get 3-dimensional objects with, you know, these kind of maneuvers in many words in GRW with only the wave function. But why do you want them if you just already have this other alternative, which is constructive right away? So in your case, you have the many words, you have all this principle or structural explanation, you have all this job to do in recovering what Bohmian mechanics already has, so why are you doing that? Right.
Can I go back to the material credit?
Yeah, something else, okay. Yeah.
Well, it's the following thought, that many of us, mostly trained in physics, quantum mechanics is the most extraordinary theory we've ever seen. And for those of us trained in physics who also then go into philosophy, the major project is to interpret, make sense of, understand this extraordinary theory, the greatest that's ever been. So that's what a lot of us are doing. Now, an alternative thing to do is to create an entirely new theory,
Right.
which is actually extremely limited and can't actually cope with experiments. David will be talking about this, I think.
Yeah.
So you're in that latter camp.
I am in
That latter camp. You want to create an entirely new theory,
no, I mean, I don't want to
which
do
doesn't
it.
actually account for any of the experiments that we actually perform.
Why do you say that?
Well,
He's going to say
David's
that.
talk.
Right, but I don't want to necessarily I mean, I'm
Yeah,
not
just-
stuck in my position forever. I mean, you can convince me otherwise. I mean, I started off with many words too, and then I changed my mind. I can change it back, maybe, I don't know. I don't think so, but...
Well, that would please Lev. Myself, I value foils. Anyway, look, I think I've made my point.
Right, yeah.
Thank you. So if you were to be presented with a version of many worlds which had as its basis a 3-dimensional ontology, spatially localized object fields, I'll say, would that bring you back to many worlds?
I mean, a many-word theory,
I know
like,
you can't
yeah,
answer that.
three-dimensional, I mean, a theory with a 3-dimensional ontology, yeah, I mean, in which what you do is a constructive explanation, yeah, I mean, but it's not about my preference necessarily.
I
mean, it's just
understand,
like,
but...
yeah, I mean, I would have less trouble understanding that theory. I would have more trouble understanding, you know, the need of many words on top of having already a 3-dimensional ontology, if you can do that otherwise. But I mean, my talk was not necessarily about convincing you about what I believe at all. I was just trying to figure out, I mean, what kind of stuff we want from a theory. So, I mean, I just don't, I mean, I didn't argue for my position at all, so.
No, I didn't mean to make this a personalist thing.
Yeah,
but
that's okay.
I would say that there are certainly people doing many worlds who also favor of a constructivist way of doing things, and
Good.
particularly having three-dimensional ontology, and so that certainly does exist.
Yeah, yeah. So I mean, I didn't even say that I don't like, you know, principal explanation. I mean, now, you know, I need to think more about this structural type of explanation that David and Simon was telling me about. But I mean, you know, it's interesting to know where the disagreement is, if there is one, which exists, of course.
I'm a
okay.
little puzzled.
Okay.
It doesn't fit my scheme.
It doesn't. Okay.
But maybe it's the first you discuss this. You say there is many words this way, boom, other way. And philosophically, they kind of all good. But I'm as a physicist. I'm looking for some reasonable physical theory.
Yeah.
And the many words looks for me is only reasonable. And I don't like principal theory. So in a sense I would like, but I don't think we have quantum mechanics on this level. For me, it's completely constructive theory. I have this Schrödinger equation, period, and I have a wave function evolving according to it. This is a whole story. This is a whole physics. All physics is extremely well defined, like Arve said, and it's evolved, and it's empirically adequate.
I know.
Because if I'm in my world, you say that there are macroscopic objects in superposition, we don't see them. The theory tells us we'll not see them.
Yeah.
We are not supposed to. So this is the simplest physical, this is the cleanest, most elegant theory which explains all what we have seen until 10 digits without introducing anything else. And I don't understand why I say principle. I completely, David already told you about energy. I don't have any energy principle. Right. I have only, it's come out. I have one equation for the whole universe. This is what I have, and it's empirically adequate. Well, what else? What else do I want?
All right. So yeah, I mean, forget about if that throw you off, just forget about that name. All right. So what to me, you had the slide before in which you said, you know, you Googled purpose of science or something, right? And they said, okay, we want to know how the word works, right? And some people want to know, I want to know how the word is, but I mean, no, they want to know how it works. That's exactly what I mean, right? You are committed to that kind of explanation, right? You want to explain, right? The macroscopic world, you save our experience. You told me many times, right? You want to save our experiences, right? Okay, so that one kind of explanation, some other people, like me, but that's okay, right? I'm not saying that you're not explaining, but I want more, okay? That's what the talk was about, right? The disagreement is, to me, is exactly in that, right? So if you're okay with, you know, explaining and saving the phenomena, yeah, many words is perfect, right? Otherwise, if you want more, right, there are people who want more, and they go completely on the different level and just say, no, I want a microscopic explanation. I want to be where all these particles are going and stuff like this, right? And then, presumably, you know, the Oxford many words, there is something in between, right, in which they're okay not to have postulating stuff microscopic. They want to have what? Oh, you can't see, you can hear. Okay, apologies. So something in between, right? And they just want to. That's what the thing was all about, right? Just like try to place people, right? So the disagreement to me is in what you want from a theory.
Just, I think it's very important kind of things to know what we want from a theory.
Yeah, and we disagree about that.
Do we want to put ourselves in the center or not? If we don't, then what I'm asking, it seems to be
But you are putting yourself, you want to explain your experiences.
No. I have a theory which has many experiences, and I am kind of very tiny there.
No, I know what you mean.
This allows me to explain also my experience. But in my theory, I'm not in the center. I don't have maximum measure of existence. Very tiny one. There are many others. I performed this this word splitting many times. So I have very tiny measure of existence.
Okay.
Thank you. I think it was a very good opening for discussion. There were just too many questions to being able to answer, and it's a good sign. So just before we go to coffee, let me just remark that we have every day of the workshop, there is going to be a discussion session, and today at 5 we are going to have a discussion session about the notion of a world. And if you want to present, please just send us an email just to give 3 minutes, 5 minutes about this issue. And to start the discussion going. So there is the email of the workshop. I think it's mwiconference@gmail.com. So feel free to, if you have something relevant, just send us an email. We'll put you on the list, and we'll continue the discussion at the break and the other talks, and then also in the evening. Yeah, it can also be a PowerPoint, but it doesn't have to be a PowerPoint. You can come and just print. Okay, let's have coffee and we'll check that.